Hello, test. Okay.
So today I'm very happy to invite Professor Luca Carlone, and he is very famous in SLAM. Especially, he got so many best awards last 5 years, and I met him in, I guess, 2019 in his class, and also in the last day, the students have the competition for the race car, right?
Yeah.
And he's a director of the Park Lab. I'm very impressed with his work on the Certifiable correct algorithm for SLAM. So let's listen to talk. Welcome.
Thank you so much for the kind introduction. It's a real pleasure to be at SNU today and give this presentation. I'm going to talk today about 3 main ideas. First of all, this is covering the group we've been doing as a group, the work we've been doing as a group on next generation robot perception. I'm going to touch on 3 main ideas, which are hierarchical representations, certifiable algorithms, and self-supervised learning. And I'm starting with this slide, just with all the pictures of the students, postdocs, collaborators, which are making this work possible, just to give them credits. I want to keep this a little bit informal. So if you have questions as I go during the presentation, just raise your hand and ask if something is not clear. So again, I want to touch on hierarchical representation, certifiable algorithms, and self-supervised learning. So maybe a good way to start is to tell you what we do as a group. As a group, we work on 3D perception and vision-based navigation. And in this slide, I'm just collecting a number of projects we've been working on, describing the motivating applications, the applications that are motivating our work. In a nutshell, we care about applications which are safety critical, high integrity, and highly interactive. Just to give you a few examples, search and rescue and autonomous vehicles are applications which are safety critical. If the navigation system on the robot fails, we can fail to search and to look for survivors. If the vision-based system of a self-driving car fails, our self-driving car might crash. Okay? So these are safety-critical applications. We've been pretty lucky over the last few years in having first-hand experience on these applications. For example, in terms of search and rescue, we've been working on the DARPA Subterranean Challenge, which is a DARPA challenge in which we had to deploy robots to explore very complex underground environments. And we went in collaboration with JPL and Caltech. We took part in the competition, actually won first and second place in 2 of the 3 events of the competition. For autonomous vehicles, we've been lucky in collaborating with NVIDIA and Ford just to get real data from self-driving cars and test our algorithms. The example on the top right is an example of high integrity application. So these are rockets or balloons. Maybe there is no human on board, so it's not safety critical, but these are very expensive pieces of equipment, so you want to make sure you don't break them. At the bottom of the slide, I'm listing what I call highly interactive applications. These are all sorts of interaction. Can be interaction among multiple robots, can be interaction between the robot and the environment, or can be interaction with humans. I'm not going to talk about that, but we have a lot to work on interacting with the environment and on soft aerial manipulation. So we have essentially drones which are able to grasp objects at high speed. I'm not going to touch on that, but that's another interesting line of research we have been working on. So by working on all these projects and applications, we got to think about different dimensions and research gaps that there are currently in perception. And I'm organizing a little bit the perspective of the different dimensions of research along 3 main directions: robustness, scalability, and scene understanding. So we would like algorithms and systems that are more robust to outliers, noise, or changes within the training domain and the test domain. We like algorithms which are more scalable, very large scenes, or going beyond the training domain. So these are pretty interesting and pretty understandable axes. What I mean by scene understanding is that we would like robots which are a little bit smarter, which are human-like. Okay? So the traditional interpretation of in robotics is that I have a robot and I tell my robot go to position X, Y, and Z. That's not the way you interact with people, right? We like robots which are a little bit smarter than that and that will be able to execute complex high-level instructions, such as robot, go grab me the cup of coffee on the desk. And in order to get that level of autonomy, robots, of course, will need to have better scene understanding. Okay? So we want to push in these three dimensions. Maybe to clarify this a bit better, let me put a bunch of data points here. If you look at the state of the art, there is a lot of work done on SLAM, simultaneous localization and mapping. Traditional SLAM is essentially geometric understanding, 3D reconstruction and geometric understanding of the scene. So SLAM is getting very robust. You can download existing systems, you can deploy in new environments that will work pretty well. Very scalable. In this example, this is a multi-robot SLAM example, which is covering tens of kilometers of trajectories, so can get very large scale. But if you look at the vertical axis, SLAM does not have a lot of scene understanding. SLAM will understand the geometry, but will not understand much more than that. At the same time, with the recent progress on deep learning, we have fully supervised baseline. We have supervised methods which allow for semantic understanding, both in 2D and in terms of 3D objects. And in this case, of course, we get a much better, much higher quality of scene understanding, but the price we pay is that these approaches typically will only work in the training domain, so the robustness of these approaches and the scalability will get much lower. So where we want to get to is clearly getting the best of all these dimensions. We would like to get an approach or a system for perception which is scalable, robust, self-supervised, and allows real-time scene understanding. And today I'm going to tell you about the work we've been doing towards that goal. So the talk is structured in 3 parts. In each part, I'm going to tell you about the work we're doing in pushing along one of these 3 dimensions, okay? So I have 3 parts of the talk. Each part is going to start with a slide like this. And I'm going to use the first slide of this part to summarize the message I want to convey. Okay? So if you want to pay attention to a few slides, look for the 3 slides like this, and you will get a good idea of the message I want to send. So the first message I have is that highly interactive and scalable robot perception requires metric semantic, hierarchical map representations, and spatial perception systems to build them in real time. Okay? So we need metric semantic and hierarchical maps, and of course we need algorithms to build them in real time. So the need for metric semantic map, I don't think I have to put too much effort in convincing you that we need metric semantic map. So imagine that I want to ask my robot, go grab me the cup of coffee on the desk. In order to execute this instruction, the robot will need to know about geometry, right? We'll need to know how to avoid obstacles, how to get close to the desk, how to avoid the desk maybe. And we'll need to know about semantics. What is a cup of coffee? Where is the desk? What is the desk? Therefore, we need map representations which are summarizing both geometric and semantic information. Therefore, back a few years ago, this is work we started probably in 2018, we started working on Chimera, which is a real-time library for metric semantic SLAM. How many of you are familiar with SLAM in this room? Okay, maybe half of you. So simultaneous localization and mapping essentially is the process of starting the robot in a completely new environment and building a map of the environment as the robot goes. So what Chimera does is pretty simple, at least in terms of input-output. Chimera is taking a bunch of images from a camera, a standard camera. The camera is going to produce also inertial measurements, so measurements of acceleration and rotation rates. And from this sequence of images, Chimera is going to build a 3D reconstruction in real time, on the fly. And this 3D reconstruction that you see in the video is actually a 3D mesh. So it's a 3D model where each phase of the mesh is color-coded. So the colors here are not real colors, but correspond to semantic labels, correspond to, essentially each color is a different type of object. Yellow are the cubicles, green are the chairs, gray is the ground, and so on. So this is metric semantic mapping. So again, Chimera is something that we provided a few years ago. Maybe the most important bit of information is that the implementation is open source if you guys want to use it, but I'm not going to discuss the details. Essentially, it's a combination of traditional SLAM and 3D reconstruction and use of 2D semantic segmentation in 2D, which gets back projected on the mesh in 3D. I want to spend a little bit more time discussing about why we need hierarchical representations instead. Okay? So we should be all on the same page that we need metric semantic representation. Why do they have to be hierarchical in nature? To convince you that we need hierarchical representations, I will consider a small example of an apartment, and I will compare a non-hierarchical, a traditional representation with a hierarchical one, and I will show you what is the advantage in getting there. So imagine that you have this apartment. I want to do a 3D map of this apartment. A non-hierarchical or flat metric semantic map of this apartment will look like this. So this is a voxel-based map. It's just an example of potential representation. It's a voxel-based map in which essentially you're representing the 3D scene as a collection of voxels, which are like small cubes. And remember that this is a metric semantic map. So not only we are describing the voxels, corresponding to the obstacles, but we are also attaching some semantic meaning to the voxels. So for example, we are telling that a specific voxel is an obstacle, but is also a bed, is part of the bedroom, is part of an apartment, is part of a building, and so on. So we are attaching all these labels. And of course, we'll need to do that for all voxels in the map. Well, from simple, back of the envelope calculation, you realize that the memory requirement of such representation scales with the number of labels, because you have to store labels for each voxel, and with the number of voxels. So V over delta cube, V is the volume, delta cube is the size of the voxels. So V over delta cube is the number of voxels in the map. So for a map of an apartment, this number, L multiplied the number of voxels is not terrible, because L with current deep learning is maybe in the order of 200 or few hundred. And the number of voxels, this is a small scale apartment, it's not going to be huge. But here we're thinking really about the future, the next generation of robot perception. So we have to imagine that we have robots with a much broader vocabulary. Okay? So in the English vocabulary, there are around 500,000 words. So now you have to imagine that L, the number of semantic labels, can become 500,000, can become very large. And we want the robots to operate over very large scales. We want to operate over tens of kilometers. And if you do the math of covering an area of 10 kilometers by 10 kilometers with a voxel size of 10 centimeters or so, this number will easily get in the billions. Okay? So if you get billions multiplied 500,000, this number will explode. So you don't want really that kind of complexity in your map representation. Trivially, if you move to a hierarchical representation, first of all, concepts in man-made environments will naturally lend itself to be organized hierarchically, because we can just say that certain objects we can group objects into rooms, we can group rooms into apartments, apartments into buildings. So naturally, there is a hierarchy because of the way these concepts are defined. And trivially, if you, instead of storing naively the semantic information, you store them hierarchically, you get a much better complexity in terms of storage. Okay? So the complexity will still depend on the number of voxels if you want to store the voxel map, but the top part of the map representation will have a much nicer complexity compared to the one that I was listing on the left. Okay? So long story short, we can essentially store the same amount of information, but we can store that with less memory. Moreover, if you think about the map as a graph, as a hierarchical graph, it becomes very easy to capture relations in this graph. For example, I'm already using the edges to represent relations, for example, between objects and rooms. So for example, an object is in a certain room, but I can also say, maybe I can say that two objects are nearby, or the kitchen and the dining room will share a door, right? So you can use the edges in the graph to represent relations. Another point I wanted to make is that you can also be more clever about, instead of storing the voxel-based map, which is very heavy, you can also store just maybe a topological map of the environment, which is this graph in black, such that the complexity of storing the representation becomes even lower. So with hierarchical map models, we can have hierarchical map models will scale better in terms of memory requirement, will allow to capture relations through the edges. And also there is a more technical point here, which we make nicely in the paper. And here I'm just going to mention, but we demonstrate in the paper that these hierarchical representations have low tree width. The tree width of a graph is a measure of complexity. So essentially, if you have graphs with low tree width, you can do fast inference over them. So we prove that if you organize things hierarchically, you will have graphs with low tree width for which you can do efficient inference. Now, for many of you doing deep learning, you might say, we don't care too much about this probabilistic inference. We are doing maybe graph neural networks, or we're using more modern tools. Well, in a few slides, I'm going to show that actually, even with graph neural networks, the expressive power of graph neural network, of some classes of graph neural networks, will depend on the tree width of the graph. So the fact that you have a low tree width in your representation is good news, independent on what is the tool you're using for inference. So all this reason, all this motivation to push on hierarchical representation led us to develop this idea and to develop algorithms to build 3D scene graphs. So 3D scene graphs are hierarchical map representations in which you have a graph with multiple layers. At the lowest layer, you have traditional dense map models. You can think about these as the 3D mesh that I was talking about before. But as you go up in the layers of the representation, you're abstracting information in terms of objects and agents, rooms, buildings, and so on. The layer which is a bit more mysterious is layer 3 of places and structures. This is a topological map, so it's a graph in which the nodes are free space and the edges correspond to traversability. So essentially, that graph of places is encoding wherever the robot can go, and structures are essentially the walls, the ceiling, and the floor of the environment. Okay? So more formally, a 3D scene graph is a directed graph where nodes are spatial concepts, anything that lives in 3D, and edges represent relations between different concepts. The reason we like so much this representation is, as I mentioned in the previous slide, this is a hierarchical representation. So it's more scalable, it's efficient for inference, and it's great at capturing relations. But also for those of you working in mapping, you can realize that this representation is including the 3 main representations we use in SLAM over the last 20 years. There is a dense metric representation at the bottom, the mesh is a dense metric representation. There is a landmark-based representation, which is the layer of objects, and there is a topological map, which is the layer of places. So in a single representation, we're encompassing all the map models used in robotics. And this representation is actionable. If I provide this map model to my robot, the robot will know about rooms, will know that there is a kitchen maybe, will know that there are certain objects in the kitchen, so I can tell my robot, go to the kitchen and pick up a cup of coffee. Of course, over the last few years, we just didn't come up with a representation. We developed algorithms to build this representation in real time from sensor data. So the algorithms, I'm going to present the algorithms and the system that we designed in 3 steps. I'm going to describe how to build the odometry part of these models, how to do loop closures, and how to populate semantic aspects. Okay? Let me start with the first one, which is the incremental construction of an odometric scene graph. Okay? So imagine that you start the robot in a new environment. The robot has no idea, has no prior knowledge about the environment. As the robot starts looking around, is able to build the 3D mesh of the environment in real time, is able to estimate its own trajectory, odometric trajectory, is able to figure out So more than the reconstruction itself in this video, what I want to stress is that everything here is happening in real time on a robot with not much computation on board. And the important bit of this slide is the table, with the runtime. The runtime here is to run Hydra, which is our system to build a 3D scene graph, on an NVIDIA Xavier, which is a small, computer on board our robots. And this is the runtime of constructing the different layers of the scene graph, which is tens of milliseconds. It's really fast in practice. So far I told you how to construct the scene graph incrementally as the robot goes, and how to do loop closures over the scene graph. So far the result is that the robot is getting around, is exploring an environment, and is able to build this representation. In the original proposal in the original paper about this, we are even able to track the poses of humans moving around, so you'll see the silhouette of humans, because we're tracking humans as well. But if you look closely at this map, there is something missing. We have the semantics of the objects, because we have the mesh, right? So we can reconstruct, we know that this is a chair, this is a couch, and so on. But if you look at the top level of this scene graph, essentially we know that there is a building, because there is a node B1, and we know the room numbers, but we don't know yet if a room is a bedroom, if a room is a kitchen, because essentially our robot cannot measure the information about the type, the semantics of the room. Which leads me to the last part I want to cover for this 3D scene graph part, which is organizing information as a graph makes it easy to infer missing labels. Okay? If you have now a graph representation, we can do some inference over the graph to infer the labels which are missing. And in particular, what we want to do is that we are given the labels of the objects in the scene graph, and we want to infer what is the label of the rooms and the buildings at the top. This is something that as humans we can do very easily. For example, if I tell you that in a room there is a bed, there is a book, there is a chair, most likely you'll be able to infer that that room is a bedroom rather than a kitchen, right? Because there is a bed. So we like to do pretty much the same for a robot, some algorithm that is able to infer missing labels from the object labels. You can use traditional techniques to do that, some probabilistic graphical models. It's a lot of things that you have to hard code. So the more modern baseline, the more modern alternative would be to use graph neural networks. How many of you are familiar with graph neural networks? Not many, maybe 20% or so. Okay. In graph neural networks, you start with a graph. Let's say that in your graph there are 4 objects in a room, and essentially you are given the labels of these 4 objects, and you want to infer the label of the room. What you do is you do some message passing. You extract some local information between the nodes, and the goal of this message passing is to form an embedding, a vector for each node, and then you classify this embedding into a label. For example, the label can be bedroom, kitchen, and so on. So graph neural networks, you can just use PyTorch, and download a number of models. What we did is to propose a slightly better model for graph neural networks. And in particular, we propose this idea of neural tree. The idea of neural tree, I'm going to cover this in a single slide because it's a very effective idea, but also a very simple idea. The basic idea that we propose is that you do not have to do message passing on the original graph. What you have to do is to transform the graph into a tree, and then do message passing on the tree. And there are algorithms from graph theory which are called tree decomposition, which will allow you to do this conversion. Okay? The tree decomposition essentially will take the graph and will partition it in subgraphs, such that these subgraphs will form a tree, and then you can do message passing on the tree. What we show is that if you do this very simple trick, just 1 line of code, essentially you get much better theoretical guarantees, and you get much better performance in practice. So, in this slide, I'm going to cover a little bit of the theoretical results and the practical results. I will not go into the details of the theory, but the theorem is essentially saying that if you have an arbitrary probability distribution over a graph, and if you consider the classes of function that the neural tree can produce, essentially you can approximate any probability distribution f with the neural tree G up to an error epsilon, so you can approximate with the error that you want. And to do that, you need a number of parameters, let's say the number of weights in your neural network, which is this capital N. And the number of parameters is proportional to the number of nodes in the graph, which is the N, linearly. So that's not bad. Like, essentially the number of weights will scale linearly with the size of the graph. And will only scale poorly in the tree width of the graph. So the tree width in this very complex expression is this TW that shows up somewhere. So the exponential dependence is on the tree width. Essentially, if you have graphs with low tree width, you will need you will need less parameters to approximate any probability distribution. But if you remember from a few slides ago, we essentially proved that scene graphs will have a small tree width. So this means that we don't need many parameters. We don't need big neural networks to perform inference and to approximate arbitrary distributions. More interestingly, if you do just evaluation in practice, you can consider standard 3D scene graph dataset, and you can test the accuracy of the prediction of the labels. So the numbers that I'm showing in this table are the percentage of nodes that we predict correctly. So ideally, you would like for this to be 100%. Okay? And I'm comparing different types of message passing, so different ways you can do message passing. And I'm comparing doing message passing on the original graph. That's the state of the art in graph neural networks. And you get decent percentages of correctly predicted nodes. And comparing these with the neural tree, in which you do this trick of converting to the tree and doing message passing. And just by doing this simple trick, you can see that the accuracy is improving by a substantial amount, 10% or even more than 10%. So what is the final result of all this? With Hydra, which is again the name we are giving to our system for building 3D scene graph, we are deploying a robot in a completely unknown environment, in this case in a kitchen. The robot is building a map of its surroundings, is estimating its own trajectory, is figuring out that there are objects, bounding boxes for objects, is figuring out the idea of the objects, and then this neural tree is inferring that from certain objects, the robot is most likely in a kitchen, and is inferring the room types for the rooms that the robot is traversing. In this case, the robot is traversing an apartment in which is starting from a room, is going upstairs to the second floor, and then is coming back and visiting the basement, I think. Okay. So we can do all these in real time. So before moving on to the next topic, I want to spend just a single slide. So now that we have these 3D scene graphs, what can we do? Why do we care about 3D scene graphs? The truth is that we believe that there are so many applications. In general, 3D scene graphs are great representations for things like task and motion planning, human-robot interaction, visual Q&A, monitoring, prediction, and so on. Many, many applications. So there is a lot of work to be done. What I'm showing in this slide are just 3 applications we tested over the last few years. The first one is hierarchical planning. Now that we have a hierarchical representation, can we use that to make motion planning faster? So imagine that a robot has to plan a path from point A to point B. And this is a very large scale map. So there is a map that, depending on the road is stable, can be a single building, 2 buildings, or 6 buildings. So very large scale map. So this is the time it takes to do standard motion planning, let's say an A-star algorithm over the voxel-based representation. So it takes, thousands of seconds, not real time. But if instead you start to use the scene graph for planning, you can plan first at the level of buildings, then at the level of rooms, and then the level of places, and you can break down the complexity of planning in a fraction of a second. So if you use the hierarchy for motion planning, you can get much faster performance. The second thing that we tested is object search, but more broadly we tested the use of scene graphs as a model for reinforcement learning. So imagine that I feed the scene graph to a reinforcement learning network, and then the reinforcement learning network is deciding the action that the robot has to take. We do this for an object search application in which the agent has to search for objects of interest in the environment, and we show that just by using this model, this very rich model of the environment, we get much better object search compared to pixel-to-action type of reinforcement learning approaches. And we also finally show that we can use this for multi-robot systems. Imagine that 2 robots are building scene graphs. They do not have much bandwidth to communicate the scene graph. we show how to do compression of these representations to reduce the amount of communication they need. The intuition there is that if one robot is building the scene graph and has to communicate to the other robot without having too much bandwidth, maybe the robot can just say that there are a bunch of rooms and can say like, just few bits of information instead of communicating a very large model. Okay, so hopefully so far I convinced you that we need metric semantic hierarchical representations for scalable robotics. Now I'm going to switch gears and I'm going to talk instead about this idea of certifiable algorithms. So the second message I want to send for today is that safety critical and high integrity applications require certifiable estimation algorithms that are able to distinguish correct estimates from incorrect ones. Okay? So what I'm talking about, imagine that you have a self-driving car, you have your algorithm, perception algorithm are estimating a bunch of things, for example, the location of other vehicles around the car. You want some algorithm that is certifiable, that is able to understand if the detections are correct or not, because if you're getting the detections wrong, you can crash. Okay? Very simple. So this part is slightly more technical, but I think will be interesting for many of you. So the basic observation is that in the background of the nice videos I was showing in the first part of the talk, essentially we are just solving a bunch of estimation problems. We are solving estimation problems for detecting objects, both in point clouds or in camera images, and we are solving estimation problems for figuring out the trajectory of the robot or like doing SLAM, for example. And the nice thing is that all these estimation problems, despite the diversity of applications, can be modeled using a single formulation. The formulation is the one that I'm showing here, is what is called the maximum likelihood formulation or maximum a posteriori formulation. Essentially, you solve the estimation problem as an optimization problem. In this optimization problem, you want to figure out some variable x. For example, you want to figure out where is the car in the image. Given a bunch of measurements y, for example, this can be a bunch of detections of key points on the car, and you're finding the x by minimizing a residual error function r, which is a given function measuring how well the x is fitting the measurements. And of course, in practice, you will have a set, large set of measurements, a bunch of different measurements. So this is just a nonlinear least squares problem. It's a very standard problem. What is the issue in practice? Well, in practice, the issue is that many of these measurements, y, will be wrong, right? Why they are wrong? Because maybe you want to detect points on your car, but the algorithm that you're using for detecting these points is getting a bunch of points which are not even on the car, or maybe the algorithm is telling that this is the wheel, but it's not the wheel, so you will have a bunch of bad detections. And for SLAM, this happens all the time. Like, if you're going around and you want to do loop closure detection, your loop closure detection algorithm will have a bunch of outliers, a bunch of false positives, which are incorrect loop closures. So we have to figure out the challenge is that we have to figure out the x, but there is a subset of measurements y which are completely wrong. There are outliers, what are called outliers. So people in robust statistics back in the 60s or the 80s told us that the way to address outliers is to replace this squared norm with a robust loss function. Okay, we just have to put a better robust loss function there. The issue is that people from statistics didn't tell us how to solve the optimization problem. Okay? It turns out that for common choices of the raw, the optimization problem becomes provably difficult, provably hard to solve. This didn't stop people in robotics and vision. I'm listing and oversimplifying, but these are the two typical approaches that you see in robotics and vision. In robotics, people really like local solvers, for example, gradient descent, Gauss-Newton, Levenberg-Mackard, in which you start from an initial guess and you just go downhill to minimize the function. Well, the issue is that in many of these applications, you do not have a good initial guess, so you don't know where to start the optimization. And also that this local optimization is easily stuck in local minima, which are bad solutions. On the other side, people in vision really love RANSAC, which is a nice algorithm based on sampling. The issue with RANSAC is that RANSAC will fail with high probability if you have too many outliers. So it will not work if you have too many outliers. And also RANSAC is designed for low-dimensional problems. So RANSAC will not really apply to problems like SLAM, for example. But the thing that bothered us when we looked at this, the state of the art, was that both algorithms will fail without notice. So this algorithm will give you an estimate, The estimate can be completely wrong, but they will not be able to tell you that the estimate they are giving you is wrong. So this led us to think about this idea of certifiable algorithms. Certifiable algorithm is something very simple. It's an algorithm that is computing an estimate and is either certifying that this is an optimal, this is the best estimate you can get, or is detecting failure otherwise. So it's either giving you an estimate or it's telling you, I'm not sure about this. The truth is that we've worked on this for the last 5 years or so. We do not have a single algorithm. We have really a toolbox of algorithms. We have algorithms based on graph theory to identify and prune very bad outliers. We have algorithms based on some trick from optimization, which is called graduated non-convexity, to empirically solve better this optimization problem. And we have algorithms based on moment relaxations, which are solving this problem with performance guarantees. So these approaches will either tell you that you got the best solution or will detect failure if they didn't get the good solution. So for today, it's more mathematical, but I would like to tell you about the moment relaxations because it's a tool which is less well known in robotics and is a very powerful tool. Before I get into the mathematics of moment relaxations, I want to spend a slide about the practical results. So this is the payoff. If you're doing the math right, this is the payoff you get. So this is some of the example of the work we have been done and the algorithms we developed over the last few years. We develop algorithms for pose estimation in point clouds, pose and shape estimation from RGBD data, and SLAM. And in each of these columns, I'm summarizing the robustness of these algorithms. So we have algorithms which are robust to 95% random outliers that run in real time. 95% outliers means that I'm giving you 100 measurements. 95 of them are complete garbage, but the algorithm is still able to find the right solution from the 5 measurements which are good. So algorithms which are tolerant, which are robust to an extreme percentage of outliers, and they are running in real time. And indeed, these algorithms, right now, are part of standard libraries. For example, our work on robust postgraph optimization is in GTSM, but also MATLAB decided to include that as part of the navigation toolbox. So it's included in standard libraries at this point. So if you do the math right, you will get better results. Hopefully that will motivate you to follow maybe the next 3 slides or so. These are more mathematical, but the tools I'm going to describe are very general. So if you're not doing estimation, if you're not doing robotics, chances are you will be able still to use this approach or these ideas because I'm going to use very general tools from optimization, which are not well known in robotics. So what we want to do here is to solve some robust estimation problem. Again, we want to solve an optimization problem in which we want to figure out the variable x and given measurements y, and all the other functions are known functions. And this is a difficult problem to optimize. So our first insight is that for typical choices that show up in robotics of the function rho and the residual function r, we can do a nice trick of reformulating the original optimization problem into a polynomial optimization problem. What is a polynomial optimization problem? Is nothing scary. It's just an optimization problem where the objective P and the constraints H and G are polynomials. x1 squared plus 2x2, just real polynomials, standard polynomials. So we show again for common instances of this problem in robot perception, you can transform this problem, you can rewrite this problem into a polynomial optimization problem. How do we do that? Well, just by inspection. Essentially, we take a long list of problems that we find in robot perception, single rotation averaging, multiple rotation averaging, post-graph optimization. So all the problems which are at the basis of calibration in robotics, SLAM, object pose estimation, we take all the problems in the state-of-the-art papers, and we show that you can rewrite the math in terms of polynomials. Okay? Let me give you just an example. If you look at the standard formulation of 3D registration, we were chatting about this morning. So you essentially have 2 sets of points, P and Q, and you want to compute a rotation and translation which is aligning these sets of points. Well, if you stare at this expression, you realize that essentially the cost function is quadratic in R&T, so it's a polynomial of degree 2. And if you stare closely at the constraints, SO3, that's a little bit more technical, but SO3, you can write it as a set of quadratic equality constraints, which are again polynomials. Okay? Not immediate as for the objective, but essentially you can rewrite both objective and constraints as quadratic polynomials. This is the case in which I have a quadratic loss function, but I said I want robust loss functions. So what we did is to show that for several choices of robust loss function, and in particular the 7 choices that I'm showing in this slide, you can put the raw, like you can choose one of these raw robust loss functions, you still get a polynomial. Okay? These choices of robust loss functions are truncated least squares, like bunch of very common loss functions. I will just pick one because it's very intuitive. So in truncated least squares, for small errors, you have a quadratic function, meaning that you do no linear least squares for small errors. But if you have large errors for a measurement, you just have a flat function, meaning that you downweight essentially the influence of that function. So how do you write this guy as a polynomial? Well, it turns out that you can just write this cost function by using binary variables, theta, in which the theta, in a nutshell, is deciding whether you are in the quadratic region or in the flat region. And you can mathematically write the function, the TLS function, with this theta. So if before you had a quadratic polynomial, right now you have a cubic polynomial, but it's still a polynomial. Okay? So again, we take common problems in perception and common robust loss functions, and we manipulate the math to show that we can get a polynomial optimization problem. Very elegant, very general, but not yet very useful computationally, because it turns out that polynomial optimization is still hard to solve. You can write many, many problems as polynomial optimization. You can write binary optimization, combinatorial optimization as polynomial optimization problems. Is a broad class of problems which are still hard to solve. This is where the second insight comes. The second insight is that for polynomial optimization, there is a very systematic way to convert the polynomial optimization problem, which is hard to solve, into a convex relaxation, and in particular a semi-definite relaxation, which instead can be solved in polynomial time, can be solved efficiently. Okay? And this is using a tool which is called the Lasserre hierarchy of moment relaxations. How many of you have heard about the moment relaxations? I know at least one. Yeah, this happens wherever I go, very few people, in every single room of the seminar I gave over the last 3 months, maybe 3 people in the room know about this. And this is why it's so important. It's a tool that is not known in robotics. There will be many, many opportunities to do novel contributions using this. The tool I'm going to describe seems scary at first, but I will show you in one slide that is a very simple idea. So hopefully we'll help you, just see that mathematically is a very simple idea. It's not anything complicated. So the goal is that I want to take a polynomial optimization problem, again a problem in which both I want to optimize over a vector x, both the objective and the constraints will be polynomials. I think for this example, I will not consider inequality constraints, I will just consider equality, but the framework can be extended to inequality constraints. And also for the sake of this explanation, I'm going to assume 2 things. I'm going to assume that the unknown, the x, is 2-dimensional, x1 and x2. Just for an example, in practice we solve problems which are very high-dimensional. And the second assumption is that the degree of the polynomials showing up in this formulation are degree up to 4, which is true, is what we see in the problems we are dealing with. So that's a realistic assumption. So what the moment relaxation will tell you is that you have to do 2 steps. The first step is to define the moment, the monomial basis. The monomial basis is just a vector in which you rewrite your unknowns, x1 and x2, but instead of considering just the 2 unknowns, you consider all the monomials function of that unknowns from degree 0 to degree 1 to degree 2 in this case, but you can decide which degree you want to stop. That is what is called the order of the relaxation. In this case, I'm stopping at order 2. Therefore, I'm considering all the monomials of degree 0, 1, and 2. Okay? So the vector is just a reparametrization. Essentially, instead of just computing x1 and x2, now I say I want to compute a bit more. I want to compute also the square of x1, the square of x2. I'm computing, I'm over-parameterizing the problem. So this is the monomial basis. The second step is to define the moment matrix. The moment matrix is just the monomial basis vector by itself. Looks like a scary matrix, but if you stare at it, the bottom line is that this matrix will contain all the monomials of your unknowns from degree 0 to degree 4. Okay? So if you stare at the entries of these, you will find all the monomials from degree 0 to degree 4. And again, these are all unknowns. We still have to compute those. But now the insight of the moment relaxation is very simple. The basic insight is the following. If this matrix contains all the monomials from degree 0 to degree 4, I can write any polynomial of degree up to 4 as a linear combination of the entries of this matrix. Right? If my polynomial is x2 to the 4 power plus 2x1, I can just pick the entries here, these plus 2x1, I can just do a linear combination of the entries and write any polynomial using this matrix. In other words, I can write any polynomial of degree up to 4 as a linear combination of this, linear product, linear combination of the entries of this matrix. So therefore, I can write both the objective and the constraints, which were polynomial of degree up to 4, as linear things. Okay? So a linear product between a known function C, known matrix C and the X, and a linear equality. Okay? So I converted a difficult problem into one that has linear objective and linear constraints. So what is the catch? Of course, there must be a catch, right? I'm converting a very difficult problem into an easy one. What is the catch? Well, the catch is that the moment matrix has to satisfy very specific properties. The moment matrix by construction is a vector by its transpose. So it has to be a positive semi-definite matrix. That is okay. I can enforce that as a convex constraint. But also this matrix has to be rank 1, because the vector by itself has to be rank 1. And unfortunately, that's a constraint which is non-convex. I cannot enforce that. And that's why I remove it, and that's why it's a relaxation, okay? Because I just remove this rank 1 constraint. So the relaxation drops a rank 1 constraint on the X, and therefore I get this nice problem, which is called a semi-definite program, or SDP. And Lasserre, the moment relaxation, will also tell you a recipe to add extra constraints to make the relaxation better. The extra constraints are nothing fancy. They are just about realizing that entries will show up multiple times in the matrix. For example, this guy is to be equal in the relaxation. So essentially, the relaxation will enforce the entries of the matrix that have to be the same to be the same. Okay? So just extra constraints. So as a summary, with Lasserre relaxation, we transform a polynomial optimization problem into a semi-definite program. This is hard to solve. This can be solved in polynomial time, so you can solve this efficiently in polynomial time. The properties that are making this relaxation so compelling to me are the ones mentioned in this theorem. I'm not going to ask you to read the theorem. I'm going to summarize the 2 main points. The first point is that Lasserre will tell you that if you solve the SDP and get a matrix X which has rank 1, then you can decompose that matrix into a vector, essentially, and that vector will be an optimal solution of the original problem. So if you got a rank 1 solution to the SDP, you are done. Theoretically, you computed an optimal solution to the original problem, which was hard to solve. Something magic, right? It was hard to solve. You get a provably optimal solution. The second property is that under mild, very mild theoretical conditions, if you increase the order of the relaxation, so if you make the X larger and larger, eventually you will get a rank 1 solution. So eventually, if you make the X, if you're willing to make the X larger and larger, you will get a rank 1 solution. Very compelling. Of course, this becomes less useful if you have to increase the order and the size of X to very large sizes. It becomes less useful. But the observation that I think is part of why I'm excited about this work is that in our perception problems, the relaxation is tight, meaning that the solution has rank 1 at the lowest relaxation order. So even if you have very small matrices X, if you have small matrices, the relaxation already produces rank 1 solution. So in other words, we can already compute provably optimal solutions with small SDPs, relatively small SDPs. And you can even do some extra trick, sparsifying the monomial basis. The relaxation will remain tight, but I'm not going to that. So as a conclusion, for the first time, we can solve robust estimation problems showing up in robot perception to optimality or compute a suboptimality gap in polynomial time. I will invite you to look at, we have many, many results. We've been working on this for a number of years. I'm going to spend one slide showing you a little bit of the empirical results. In the paper, we have probably 7 to 10 applications. Here I'm showing just 3 problems: single rotation averaging, multiple rotation averaging, and point cloud registration. And on this column, I'm showing the suboptimality. So this is how close to optimal the convex relaxation gets. Ideally, you would like to get 0 suboptimality, so you compute exactly optimal solutions. And here, don't look at all the complexity, look just at the blue. Just look at stride, which is our SDP solver. And you can see that suboptimality is less than 10 to the minus 10. So this numerically is optimal solution for many, many levels of outliers, from 0% outliers to 90% outliers. You can see that we can always get close to optimal solutions. And similar things apply to the other problems. 10 to the minus 10, maybe a little bit more here. Note one thing. Optimal solutions in virtually all cases, but there are failure modes. And those failure modes have to be there, because this is an NPR, is a probably R problem. We cannot expect that we solve all the instances in polynomial time. There will be instances which are hard to solve, right? But our algorithm will be able to tell you that in this case, I got this solution, but the suboptimality is not 0. So be careful, maybe you don't want to trust it. Okay? So that's the certifiability part. And on the right-hand side, I don't know, it's less relevant, but it's telling you if you get optimal solutions, this will map to rotation errors in this case, which are very good, which are good estimation errors if you can compute optimal solutions. Okay, so I want to spend the last 5 minutes or so with the last part of the talk. This is a little bit more high level than the previous two, and I want to connect to learning in the final part of the talk. The last message I want to send is that so far we had certifiable algorithms which are able to solve a problem and detect if they were able to solve the problem correctly or detect failures otherwise. In this last part, I want to connect certification and self-supervision. And the message is that certification and self-supervision are twin challenges. If we can certify correctness, we can learn without supervision. So let me give you a little bit of the context of what I'm talking about here. So far, I discussed estimation problems in which maybe I have measurements, let's say these key points in the image. Using these measurements, I solve a nice optimization problem, and I get an estimate, for example, of the pose of the car in the image. But the truth is that in practice, these measurements are produced by a neural network. The neural network will take the image in input or an RGBD measurement, RGBD data, and will produce these key point detections. So the question we ask here, now that you have much better algorithms for estimation for this block, can we use these better algorithms to self-supervise the neural network? Instead of manually supervising that with human labels, can we have our algorithms provide some supervisory signal and improve the neural network over time? This, by the way, is work that we published on TRO earlier this year, and an evolution of this work. Actually, the work I'm presenting is also something that was presented yesterday at RSS. The basic idea, I'm going to discuss the basic idea in an animation because it's very simple. So imagine that you start with a pre-trained network. So maybe you train your network in simulation. Okay? You have a neural network for key point detection, trained in simulation. This is not perfect. It's actually far from perfect. And now you expose it to real data. So you provide a batch of real images, in this case, these 3. And these are real images without labels. So they are the ones that you can face at test time, let's say. So the basic idea of our approach for self-supervised learning is that with our imperfect network, we can do a forward pass. We can predict the key points using the neural network. The key points will not be great because the neural network is trained just in simulation. We can apply our very sophisticated algorithm for robust estimation. the algorithm in some cases will get the solution right, in some other cases we get the solution wrong just because there is too much noise in input. But if you're able to distinguish the correct solution from the incorrect ones, we can use the correct solution as pseudo labels, right? So we can say this is correct, therefore I can use this information, I can backpropagate, and I can improve my neural network. Next time I can take another batch of data, I have a slightly better neural network, I do again a forward pass, this time I get two solutions being correct, I backpropagate those, the neural network is further improving, and I can keep going until I have all the solutions being correct. Okay? So essentially, whenever I get a good solution, I add it to the training data set, and I improve my neural network that way. So a little bit more into more practical terms, we apply this idea to pose estimation from RGBD data. So we have an input, an image, and depth data. We have a neural network which is doing key point detection. And after the neural network, we have an optimization problem which is figuring out a pose estimate. And what we do is to add certification blocks. We add essentially blocks which are able to understand if the solution is correct or not. And if the solution is correct, we use that for backpropagation. At RSS, we presented an evolution of this idea, which is actually if you have multiple models in parallel instead of a single one, the same idea applies. You can apply the input to multiple models, and whenever you get the solution correct, you can backpropagate and improve both the model itself and the other models in parallel. So you can self-supervise multiple models at the same time. There are a bunch of technical details, I will not get into that. What I want to show you is the typical trend you expect from this type of self-supervised learning. So here, there are the iterations of self-supervised learning. These are essentially iterations of stochastic gradient descent. And on the y-axis, there is the percentage of correct outputs. You can think about the number of times you get the solution correct. We start with a pre-trained network, which is pre-trained in simulation, and of course the success rate is very low. I think it's around 20% in this case. But as we go through the self-supervision, essentially the success rate gets better and better, again, without any manual supervision, just by exposing real data to the network. And I think what you see here in the visualization, the green one is the actual point cloud, and the CAD model is the way we are explaining, the way we are fitting essentially the model to the point cloud. So at the beginning it's very rough, but at the end, we'll get the solution right. And indeed, it turns out that we can do, with our self-supervised approach, we can do well, even compared to supervised baselines. So we can have pretty much the same performance or slightly better. Last slide, this same message, but a little bit more quantitative. So in both the table and the figure here, I'm comparing our self-supervised approach against both fully supervised approaches. COSI-POSE is a popular approach for pose estimation of objects. Another baseline for self-supervised learning. This plot, is ADD score, is a little bit complicated, but what you would like is for the curve to be as much as possible to the top left. That's the best error that you can get. And essentially what you have here is that the proposed approach is the one at the top, which is a good sign. The proposed approach is slightly better, but is comparable to supervised baselines. So that's good. We don't want to get much better than those. There is no reason to get much better than those, but we get similar performance as fully supervised baselines while we are not requiring supervision. So that's great. And we do much, much better than baseline for self-supervised learning. For example, Self-60++ is a competitor. We do much better than that. Qualitative results here, this is the input point cloud. This is the result of our approach. And this is the result of actually supervised baselines. Decent, but we do slightly better in this case. So let me maybe wrap up here with a conclusion slide. So these are the three messages that I want to send today. The first is that scalable robot perception requires metric semantic hierarchical maps, and of course, real-time algorithms and systems to build them. The second message is that safety-critical applications require certifiable estimation algorithms that can distinguish correct estimates from incorrect ones. And the final point is that certification and self-supervision are twin challenges in the sense that if you're able to detect correct solutions, we can just use them, we can just learn from them. And with this, I will thank our sponsors supporting the group, and will thank you for your attention.
Oh, thank you for your great presenting us great presentation. And I read about your paper of sparse semi-definite relaxation, and it says for applying a semi-definite relaxation or Lasser's hierarchy, square of residual function and constraint should be expressed in the form of polynomials. That's the reason why in the example of this paper, absolute post-estimation, residual function is used as point line distance, not the formal way of using the visual SLAM, that is reprojection error. But there are some residual function in the form of rational functions of polynomials, such as bundle adjustment. So what I want to ask is, just as formulating truncated least square residual into polynomial by introducing some new variable theta, can we just apply the rational function problem by, if you introduce new variables such as ratio between numerator and denominator, and multiplying the denominator to both sides of the equation, and we can get some additional constraint of this new variable rational. Can the optimization problem of rational function be solved by this method?
Great question. It's clear that you read the paper carefully, because you know that it's something we thought about. But what your colleague is asking in bundle adjustment, informally, like in bundle adjustment, there are rational functions. Is this a board? Can I write on the board? Okay. So there are rational functions like these, maybe minus maybe a term which is known. This would be just an absolute value, but let me put a norm here. And because when you do projections, essentially you have to divide by the depth. So therefore you have these kind of rational functions in which the x is the x coordinate of the 3D point and the z is the distance to the camera. And this, of course, is not a polynomial function, right? You have a rational function. Your colleague is saying, why don't we do a reparametrization in which we say that, we call that y, and then we say y equals to x over z, and then we transform this into y z equals to x, and now this is a polynomial.
Yes.
Right? Yeah. So the answer is yes, you can. But the reason why, people are saying essentially that it will not apply is that the dimension will explode. Because of this, the dimension will explode. Every single measurement that you have will be a new variable, so the relaxation will just get too large. You can do it, but it will not be very practical because the SDP will just be too large. But if you have some clever, faster SDP solver, even with this, maybe could be viable at some point. I think that there are people from applied mathematics, the same people developing the Lasser hierarchy, are also thinking about rational functions, so there might be even other opportunities in applied mathematics that we are not aware of for dealing with these functions. Yeah. Great point.
Thank you.
Did I answer?
Yeah, thank you. I'm the master student of Professor Ayang Kim. Yes.
Okay, great.
Thank you. My name is Jeoshin, by the way.
Thanks for the question.
Thank you for your great presentation. I have a question in the first hierarchical graph representation. And what kind of node feature you use for the graph neural network? I think the visual feature should be panoramic if it properly represented a point, a specific point, but it seems that the robot is just using a perspective camera. So I wonder what kind of node feature you use.
Yes, it's a great question. Let me see if I can get to that slide. So first of all, we're using typically an RGBD camera or a stereo camera, which is pretty much the same, but we have information in 3D. The neural network, the way we're applying it is that we are passing the layer of objects, and then we are forming a graph with the objects and with the rooms and the building, like, the building, maybe not even that, but, just objects and rooms. And then we're doing message passing to figure out the labels of the rooms. In terms of features we use for the objects, I think is centroid of the bounding box, size of the bounding box, and if you have the semantics, I think we tried both with one hot vector, like, with the semantics, as well as that, like, word-to-back type of representation of semantics. And that's the way, like, we initialize the message passing. For the rooms, I think we also initialize some features because we know the geometric properties of the room, like, centroid and bounding box, we also know that. So I think we use those features as well. But we do not have the semantics, that's what we want to compute for the rooms. Yeah, we do some ablation, like, for that, I think we are doing a little bit of a better explanation in the recent archive paper that we put on archive a couple of months ago, but, we have a lot of ablations there also for the features. Is a good question, yeah. Am I answering your question?
Oh, yes, okay. Thank you.
Thank you.
I am a PhD student in Robot Learning Laboratory, Professor Song-Ayo, and my name is Hyeon Yu. Thank you.
Thanks.
And any other question? Yeah.
Very interesting talk. Thank you. So today you've talked about hierarchical representation and self-supervision. What came up to my mind was a lot of people talk about the use of large language models nowadays, and languages are hierarchical, and nowadays we have stuff like CLIP that kind of replaces self-supervision for vision language models. So do you have any plans, or do you see any places for large language models to be used for, like, SLAM or navigation or perception tasks in robotics?
Great question. Like, definitely, like, I was at CVPR a few weeks ago, I was at RSS this week. Like, it's impossible not to talk about large language models. So there are several things. First of all, like, with the Chimera, let me see if I can get there. Yeah. So Chimera is something we started 2018, right? A while ago, like, language models were not even a thing. But if I have to redo this, I would definitely use, like, instead of, like, just the classes of semantic, I would use embeddings from language models just to do what is called open set, open word, like, semantic segmentation. And let me explain, like, here we have a predefined class of semantic labels, right? You have 200 classes, chairs, table, fridge, blah, blah, blah. The state of the art is pushing towards open set classification, in which I can classify any word I want with a single vector embedding. So that's something that, if I had to do this now, like, I would definitely do. And indeed at RSS and CVPR as well, there are a bunch of cool papers shooting in that direction. If you guys haven't seen that, there is, Concept Fusion, which is doing, like, similar idea. Essentially, they're building a map, but they're attaching a language clip-like embedding, like, for each piece of the map. And there is even another group from NYU, another paper at RSS on that. So definitely, like, that's the way to go, because otherwise, like, having a fixed set of classes is restrictive. There are other opportunities for language at the level of at the top level of the graph neural network. For example, here we're training graph neural networks for inferring, like, objects versus rooms, right? And we need a training data set for this. We have already a paper out there which is exploring a very simple idea. In principle, you can just query neural net, a language model. You can query in a clever way. You have to query, for example, what is the most likely room containing a bed? So the language model will have this kind of prior knowledge about, what is the most likely room for certain objects. And what we show in the paper is that if you do things like language model or vision language models, you can do this kind of inference of rooms in a zero-shot fashion. So you don't need training anymore, you just use the language model. You query the language model to get these correlations. There are many more opportunities, so definitely, like, an active research topic. Good question.
Thank you. I'm David I'm a PhD student from Professor Kim's lab.
Hi, thank you for your great talk. I'm Sang-Hong Yoon, a PhD student from Frank Park's lab. I'm not very experienced in this navigation and SLAM area, so my question may be stupid, but I was wondering if you can extend your 3D hierarchical scene graph idea into outdoor world or scenes that are not as structured as you dealt with. For example, if there's no concept of room, for things like that.
It's a great question. We're thinking a lot about that right now because we're thinking about two extensions which are very important also for many applications. One is outdoors, and the other one is truly dynamic scenes in which maybe you do not have just humans, but you have objects moving around and so on. For the outdoors, the first observation is that there is still a hierarchy. If you think about a urban environment, there will be roads, there will be blocks, there will be neighborhoods, there will be towns and so on. You still have a hierarchy there. And we are thinking about how to extend this work to that setup. There is a naive way to extend the work to that setup, which is by training a graph neural network. A graph neural network can do a classification. You start from the places, you start classifying the places into the next level, then you apply another neural network, you classify to the next level, and you obtain a hierarchy that way. We're not fully satisfied. First of all, it's very hard to build training data set at that scale, but also we are not fully satisfied just by a pure learning-based approach. We are thinking about ways to combine graph neural networks with more knowledge bases or ontologies to build in a more clever way this hierarchy. And also something that we are very interested in is to have an automatic way to come up with the layers, right? So in indoor, it's pretty trivial, right? You have objects, you have rooms, you have buildings. In outdoor, I don't want my students to sit down and say that, for the urban scenario, these are the layers. For a rural scenario, these are the layers. We are coming up with an approach which is essentially saying this is the universe of concepts you care about. This is the task that the robot has to complete. What is the right set of layers you have to care about? So work in progress. We have early results on that we presented at RSS workshop last Monday, but work in progress. I think it's a very interesting question. To be honest, in anything I said today, there is 10x more work to be done in many of the areas. And same for the convex relaxations. Something that is important to mention. So my computer is dying, but hopefully I will get just to that slide. So I told that for this idea of robust estimation, we have a set of approaches. There is a little bit of a gap in which the heuristic approaches, graduated non-convex in graph theory, are running very fast, milliseconds, real time, but they do not have performance guarantees. And instead, what I told you about today, the moment relaxation, have strong performance guarantees. They run in polynomial time, but polynomial time is not milliseconds necessarily. The SDP solvers that I'm using are still taking seconds to minutes to solve some of these problems. So there is a lot of computational work to be done to make these much faster, such that you bridge the gap between practical algorithms and theoretical algorithms. Okay? So lots of work to be done.
Can I have one more question? I'm also very impressed by your work on the robust estimation you just talked about. I think this work will potentially have a bigger impact. So across many adjacent areas. So I was wondering if your software is publicly available and can you download it and apply it to our problems?
Yeah, so we're trying to release as much as we can. Software-wise, probably 90% of whenever the sponsor allow us to release, we're putting things on GitHub. For these. Graduated non-convex, we have an implementation in MATLAB, and we implemented also in GTSAM. GTSAM is, SLAM library is very popular. Moment relaxations, we have a tutorial online on GitHub, which is in MATLAB, it's very easy to use. We have an SDP solver, which is called Stride. By the way, my student Heng Yang did a lot of this works. Lots of credits, is going to start as a faculty at Harvard, this month. Did amazing work on these topics. But yes, this SDP solver, which is open source, you can use it. is not as mature as CVX or standard solvers, but you guys, there can be opportunities for research there as well. So so everything is open source. You can start building on that. I completely agree on the reach of these tools. They are much more general than the problems we're dealing with. And indeed, best paper finalist at RSS this month, one of the best paper finalists is about applying moment relaxations for path planning. So, that tells you a lot.
Thank you so much.
Thank you for an interesting talk. I'm the master student from the Ion Kim. I have a question about the moment relaxation. You have mentioned that the existing robust loss function could be converted to the polynomial problem using the integer variable theta.
And that's true for these 7, because at least for what we know is true for these 7 loss functions. Yeah. Mm-hmm.
But in my knowledge, the integer optimization has a scalable issue since the computational assembly complexities grow exponentially. So this method works when the constraint is there are so many constraints about the relate to the robust loss function?
So I'm trying to rephrase just on this, make sure I understand the question, but you're saying the problem we start with is some exponential complexity. How can we get a polynomial time algorithm?
Not polynomial algorithm, but when we convert the TLS truncated least square function to a polynomial constraint,
yep.
The variable theta is the integer variable, not continuous variable. So this optimization problem is related to the integer optimization.
Yes.
And from my knowledge, the integer optimization has a scalable issue. The asymptotically complexities grow exponentially when the constraint is increasing. So does it work when the constraint is, there are a lot of constraints related to the truncated least squares function?
By the way, that's exactly the magic, right? The magic here is that we have a problem which has some non-convexity here, maybe here, is binary, right? It's a very difficult problem, but after you convert to an SDP, it's a polynomial time problem, right? That's exactly the magic. So several things, the first thing is that binary is polynomial. So you can write binary constraints as polynomials. For example, to say that the theta is in 0, 1, I just have to say that theta squared is equal to theta. That's the same as saying that, theta has to be either 0 or 1. Okay, so that's a polynomial. And so I can do this and I can get to the framework of moment relaxations and I convert this to an SDP. You are right that the price I pay is that now I have a variable for each measurement. So the SDP, will suffer from that because I have 1 theta for each measurement, is the price to pay. That's the price to pay. That's why, the SDP is still pretty large. The other thing that is important to mention is that you start from a hard problem, right? So in principle, you cannot expect that you're solving polynomial time all instances of that problem, just because the problem is NP-hard, okay? But the surprising thing that we see is that you can solve 99% of the problems to optimality with these tools, and it's very hard to find problems in which you have this really exponential or this really hardness, that is the theoretical hardness. Because hardness results are telling you that there is some worst case instance which is very hard to solve. Yeah. But what we see in practice is that practical problems, in polynomial time you can solve them. Right? So I hope that addressed. It's a very deep question, but I hope I'm addressing it. So.
Thanks for answering.
Professor, thank you for your speech. And I am Kyung-chan Kim from Lab for Autonomous Robotics Research. And my question is about your suggested framework about self-supervised learning with certifiably robust geometric estimation. it seems like that your framework now is based on the front end, which is based on neural network-based feature detection and some sort of things, and then the robust estimator part seems like it is not based on neural networks. But I want to ask if you think that making the whole framework fully differentiable would benefit or not. Yeah.
Yeah, it's a good question. I think we're taking a position here, which is if you use the optimization, if you know the geometry of the problem, it's better to use it rather than throwing it away. And if you have two neural networks, you will not be able to do the trick I'm showing. You will not be able to do this self-supervision. So if you have two neural networks, you will have to supervise. Instead, because essentially our estimation is kind of correcting the errors of the neural network, that's where the learning happens, right? So the first answer is that it's very important. It's very important, that you have the estimation problem to enable the self-supervision. The second answer is that, my philosophy is that whenever, learning is great for things that you don't know. We don't have a good way to do semantic segmentation. Let's use deep learning. I agree with that. But there are problems which are very well understood, like 3D registration, SLAM, and so on. So if you have working solution for those, why not using them? Maybe more of a position than a necessarily true statement. But the approach we are taking is actually to mix as much as we can learning with the model-based approaches to get the best of both worlds.
Thank you for your answer.
Thank you.
Hierarchical representation, right? You will make a hierarchy by manually or automatically?
Right now it's manual, we define objects, rooms, and so on, but we are working on the automatic version, and we have a pretty good idea about how to do the automatic version. So again, we'll connect, you will need an ontology, you will need a dictionary of existing relations, right? And then the question is how to ground that dictionary of relations into geometry. So hopefully we'll get that for ICRA. We're working on that.
And second question
Yeah.
about momentum metrics.
Yes.
I think it's like kernel method, very popular now, right? Kernel method in the machine learning. Kernel method.
Kernel methods.
Yeah,
Mm-hmm.
it's popular now.
Mm-hmm.
They could send it to the high dimensional space.
Mm-hmm.
So is it very similar to that? I think. They expand the vector and matrix.
There might be some connection. I don't know, there are also different versions of the relaxation. There is something that is called a spectral relaxation, in which you drop the semi-definite constraint. There might be some connections. I think people are also looking at connection between these and what is called the Koopman operator in control theory. So I think a lot of people in applied mathematics still investigate. Still, this was proposed in applied mathematics in the early 2000s. That it's 20 years ago, but in applied mathematics terms, it's very recent, right? So I think many people are still trying to understand, the implications of that. I'm not aware of connections with kernel methods. Would be interesting to investigate.
Momentum mastery is symmetric. Right?
Yes.
Yeah, that's why.
Mm-hmm.
So that's good.
The question is maybe low rankness versus the way you optimize, SDP versus other techniques. We can chat about it.
Okay, so
Yeah, there was a question from YouTube streaming and from Mr. Daniel Park. Can you explain more about how to catch hierarchical semantic representations? I mean, it is not intuitive for a computer to understand its bedroom just because there is a bed in a room. So is it human labeled, or did you try using large language models such as GPT to make this hierarchical representation?
It's a great question. I'm packing a lot in this presentation, so of course, many parts will be high level. The way it works is that first of all, the rooms are segmented geometrically. So essentially, the robot will go around, will figure out this graph of places, and then from the graph of places, we'll figure out that this room is loosely connected to the next room, so we'll identify this as a separate room. And at the same time, we'll also identify a number of objects in the room, tables, chairs, and so on. And then at that point, these objects are fed to a graph neural network, which is classifying, depending on these objects, is classifying this room as a conference room, for example. And the graph neural network indeed is supervised. So we have to provide a data set which is teaching the neural network correlation between objects and rooms. But I also mentioned where we have a recent paper in which we are showing how to use language model and visual language models to learn that correlation and to classify rooms in a zero-shot way. So we have both things, both on archive. Thanks.
Me? Yeah. I'm a master student from Professor Taewon Kim's and Jae-hyun Kim.
Okay, so let's not finish. Oh, we have one. The last one, yeah.
Thank you for your presentation. I'm Jisung Jung, who's master student of Professor Taewon Kim. I have one question about your hierarchical representation research. In my past research, I wanted to localize 3D object poses, but I found it is difficult with vision-based data. I'm not sure if I clearly understand. I think you used semantic segmentation and 3D point cloud data. What I want to ask is it possible to perform 3D localization from vision-based data, not using network model?
Your question is about localizing the objects, like how to use vision data to estimate the poses of objects of interest. Yeah. So there are a couple of things maybe. So we do two things which I mentioned in some slide, like, well, my computer died, so I had the battery as well, but the battery is dead as well. So with Chimera, essentially, we have this 3D reconstruction of the mesh. Okay, what you have to imagine is that the robot is doing some mesh reconstruction in 3D, and then there is a 2D segmentation network, which is telling, like, these pixels are a chair, these pixels are a table, and then Chimera is back projecting this information on the mesh, such that the mesh will have colors, right? There will be a portion which is the table, like, another set of mesh faces, which are the chair, and so on. So at that point, you can just isolate, like, the set of faces with the same label, and you will directly, like, see the table in the mesh, see the chairs, and so on. So by just clustering them, you already have a subset of the mesh corresponding to each object. At that point, we say you can do two things. If for that class of object you don't know the shape, you can just fit a bounding box, right? You have the mesh, you fit a bounding box. If instead you know the shape, you can do some 3D registration. You have a CAD model, you align that to the mesh. In the original paper, we do that in a pretty naive way. We do some feature extraction on the mesh, and we try to align things. Doesn't work great because the mesh is very noisy. The work that I was presenting on self-supervision at the very end is what we are planning to use next. We want to use these self-supervised techniques to detect key points, and then, like, use the key points actually to fit the mesh model, the CAD model. And these techniques work well, I think, for both RGBD is great, but there are also techniques for just vision-based data. So we're going to use key point-based methods to figure out the object poses. Yeah.
Thank you. Thank you for your answer.